Snowfall accumulation estimates are vital because they can provide you with simple information, like whether or not you should go into work in the morning or if there will be too much snow on the ground to risk the commute. In order to come up with an accurate estimate, models need a good representation of the snowflake geometry. This can be affected by many different variables, including the air temperature and the relative humidity of the air in which the snowflake formed, and then the air column that it fell through. It can also be affected by the turbulence of the environment as it's falling. We came up with 3 new classifications of snowflake and also investigated the turbulence environment of a previously classified type of snowflake, which we felt might not always be well represented by snowfall accumulation estimate models, given the wide diversity of shapes seen in this type of snowflake. So the previously classified type that we studied was called a rhymed aggregate. And these are basically jumbles of snowflakes which are falling together and then have tiny particles of water which freeze onto the surface of this jumble of snowflakes. Previous studies have mostly looked at rhymed aggregates that compose of one type of crystalline structure. So they may look at something which has 6-sided dendrites in it. But we also included rhymed aggregates that were composed of different crystal structures. So you could have plates, columns, needles, and 6-sided structures all in one aggregate. The first of the new classifications we came up with was a train snowflake. So these are spheres of flakes that are connected by very thin connecting crystals, and the spheres have to be roughly equal in size for this classification. The next one that we classified was an outrigger. So this was a large mass of snowflakes with another thin connector and then a smaller mass of snowflakes at the end. And the final classification that we used was a tail snowflake. So this is another large mass with an appendage or a tail coming off of it. So in order to get these images, we utilized a multi-angle snowflake camera, which is actually 3 cameras centered around an area. And when it's triggered, you get 3 different angles of the snowflake, and while it's still in free fall. So the structure is better preserved than using other techniques. Once we had these images, we matched them with reflectivity and spectral width data from an upward pointing radar. And the reflectivity is kind of like the storm intensity. It has to do with the number and size of particles that are falling. And the spectral width was used as a proxy for turbulence. So once we had the turbulence during the time of that individual snowflake that we were studying, we compared it to the range of spectral width values that we would see for a similar reflectivity value. So the box plots in this chart on the right represent the 25th, 50th, and 75th percentiles of the spectral width values that fell within 2 dBz of the reflectivity value on the x-axis. And then the individual spectral width values are plotted as the dots that you see. So we did not see a strong correlation between the low spectral width or turbulence and the formation of these delicate aggregates. In the future, we hope to also look at relative humidity and temperature to see if these variables or other sounding data may have a stronger correlation to the formation of these delicate aggregates.